Okay, so welcome to this second module on linear systems course. So as said earlier, much of the next two modules we will spend equipping ourselves with tools from linear algebra. Some of the things which I am going to tell you in the next 20 minutes or so might be a bit familiar, some may not be. As said earlier, we will still try to make it as inclusive as possible, but it might help to have some references earlier later on as the lecture goes by. Okay, I guess we all know about set theory, right? So how to define elements of sets, how to define subsets, unions, intersections, empty set and disjoint sets. So I mean, if you are not familiar, then maybe you can just go back to your earlier maths course in maybe first or second year of engineering. So I'll skip the details of this. So what I will just introduce you to the terminology which I possibly think you may not be too familiar with, or the kind of notations that we will use throughout the course, which are a little more general than what you would have learnt in some earlier set theory class. So the first thing is okay, how do we define what is called a Cartesian product? Of course, so we define it over non-empty sets. Well, it's the empty sets becomes a bit trivial, so it doesn't really make sense to define it over non-empty sets. So just take two sets A and B. So the Cartesian product is the set of all possible ordered pairs. So I'll tell you why I call this ordered. So take A comma B with A belonging to A and B belonging to B, such that, well, A cross B is represented as just this A comma B. So the order comes from the notion that A comes from so small a comes from capital A, small b comes from capital B, and so on, right. So there is nothing really that is defined over two sets. You can still define it over any number of sets. So a simple example is the space Rn, or the n-dimensional space is a Cartesian product of n sets of real numbers. So much of these things will be made clear in detail as we go by. Some other things which we would have learned maybe a bit informally is the notion of a function, and function is always or usually defined between two sets, right, which in such a way that it's a rule. Okay, this is a little abstraction, but things will be clear soon. It's a rule that assigns to each element of a set A an element of set B. So usually, you talk of A, this is a standard textbook notation. So you take a function f which associates each element of A to an element of B. Okay, so what's the formal definition, right? So I think I just take these things from this famous book on topology by James Munres. So by definition, it's a rule of assignment is a subset R, assuming we know the notions of subsets, of a Cartesian product C and D of two sets, having the property that each element of C appears as the first coordinate of at most one ordered pair belonging to R. Okay, we will just see what this mathematically means, so that the statements are a little easier to follow. Okay, so I look at C comma D is assigned, or it's associated with a rule R, and I say, but it's the same rule. If I say C comma D prime, it essentially means this one, right, that D should be equal to D prime. So there is only one unique rule that defines C and a D. C coming from a set capital C, D coming from a set capital D, right. So in general, the rule is such that it assigns to the element, but every element C of this set capital C, and element D, and denoted as the C comma D is in this rule R. Okay, so we'll do it a little more formally now, right. So then things you would have heard of, right. What is a domain of a set, and what is, or domain of a function, and what is a range. So the domain of this rule R is the set of all C's, right, such that there exists a D, right, such that this pair C and D is associated to this rule R. Okay. So this is typically a subset of C. It could be the entire set C also. Similarly, the image is also called the range is R. Again, it's typically if I just look at this picture, I would associate the domain to the left hand side, and so on the right hand side is what I will define shortly as the image. So this image is the set of all points D here, such that there exists a C which comes from C, and these C and D together are associated to this rule R. And not surprisingly, the image or the range is a subset of D. It could again as be an entire subset, entire set D2. Okay, now in general, now how do we define a function? So far we said, well, there is some rule which associates elements over here to some elements over here. Okay, so function is a rule of assignment together with a set that contains the image set of R. Okay, so the domain of the rule is the domain of the function, and the image of the rule, also called the image set of X, is called the range of F. So I will define a function F as simply something which associates elements of set capital A to set capital B. Okay, we would have done this earlier, and there is nothing really surprising here, just that it's a little more formal. So when I say okay, F is a function, it also means F is a mapping from A into B, or simply F maps A to B, right. So what does it mean in terms of the rule? So if I take an element A of A, F of A is the unique element of B. So if I just draw a little picture, so I have a here, a B, a little element of A under the function F maps to some point F of A. Right. So F of A is in B, A is an element of A, right. So this should be like unique. So F of A is the unique element of B, and in some sense also called the value of the function F at the point A, or the image of A under F, right. Or simply if I just say a rule based notation, it will just be something like this. If I just take say for example a vector x and a function which just multiplies it by say a number 3, right. So this is the simplest example of a function, right. So f of x is say 3 times x. Okay, we will just, and most of the times we will just restrict ourselves to linear functions. These are all in one dimensions. We will slowly generalize this to Rn and so on. Right. Okay. So what is interesting? So before we go to composition is, so whenever I just say a function f of x, it is, well, by definition it is not complete. So if I just say y equal to f of x, I need to really specify what is the, say, the domain and the range. So let us do quickly some kind of examples. So let us say I take a function f1, which is R to R, which is the entire space of real numbers. That's a domain space. The range space is also the entire of R, and it is defined in such a way that f1 of x is simply x square. So if I were to draw a graph of it, so, well, not surprising, this looks like it's a parabola, so I just get this entire thing, right. So this is this entire space. So my domain and range are this spanned by this entire thing. Okay, and this is my function x square. Okay, I can do something else also, right. So if I define this as say R plus to R, such that again same, the definition would still be the same, f2 of x is x square. So I am restricting my domain now. It's just, so when I say R plus, it's just I am just talking of numbers greater than or equal to 0. So essentially I am, so this is my f1. Now if I look at f2, okay, let me use a different color. So f2 would look something like this. Right, so this is my f2. Right, so I just discard these negative things because this is not in the domain. Similarly, if I define some function f3 in such a way that it goes from R to R plus, right. So I am just restricting now the range of it to to R plus in such a way that again the function is defined still in the same way, x square So now I have the graph would look something like this. So since this is the entire real line, so from positive negative values and positive values, this anyways just takes positive values. So this will just be this one. So this is my F3. And lastly, if I look at F4, which is again I just restrict them to just R plus for all numbers greater than or equal to 0 to R plus, and F4x still remains the same. And if I like draw a graph, this would, okay, how would it look like? It will just be this. Okay. So here the domain and range is this entire shaded blue line. In the second case, my domain and range would just be say this one. So I am just restricting to R plus, right? So this is my domain here, which is all the shaded region. So in the third case, again, so this is the entire real line. So this would be my domain. And in the fourth case, I am just restricting to positive numbers here. Right. Okay. So just to give an illustration of how we define functions and why the definition is not always complete unless you define the domain and the range space. Okay, we will revisit this shortly again. Okay, now something which is important is also look at compositions of functions. Say I have a function, let's say I define A to B, define a function f which associates this A, capital A to capital B, and let me also talk of C which takes elements of capital B and gives me elements in capital C with say some other function G. Now can I use the standard definitions to just generally define this function here, right, which directly goes from A to C. So I have f from A to B, G from B to C. Can I define something which associates A directly to C? Okay, so one way to look at it is, okay, so I just look at the composition of f with G. So what's the domain of this composition of this big map? So this is f composed with G. So its domain is A and the range is C. So what is the rule now for this? So the rule, if you see, the rule associates say a number from A, which is a domain space, then to the range space. So here I am looking at A comma C, right, where A is in capital A, C comes from capital C, in such a way that for some B which lies here, so this we call this A, some point C here, B here, such that f this A under the function f or the map f goes to B, such that B is now f of A. Okay. Now what does the G do? The G takes this point B and gives me a point here. So this G takes in its argument B and gives me a point C. Okay. So this is the general rule. It is A comma C for some B in this capital B, which is the image of this point f. So this point A under the map or the function f, and similarly C is the image of this point B coming from the map or the function G. Okay. So this is now the rule, right. So G, so f composed with G of A, I can write simply this as G f of A. Right, we would have done several things like this without really understanding that we are actually doing a composition of function. For example, say sine of x square, right, or even say functions like square root of 1 plus x square and several things like that. These are essentially composition of functions. One which takes associates so this number in this argument to a sinusoidal value, and one which just squares the number inside it. So these are all composite functions, and then we would remember from calculus of how we do differentiation of this by the chain rule and so on. Okay. Something which will be a little important, and again we would have done this a little informally somewhere, but let's learn this in a different way. So, let's take, I'll just talk of this general functions f going from a to b. So, this function is called 1 to 1, or more generally as an injective function if for each pair of distinct points say their images under f are distinct. So, say suppose I have a to b, say this is f, sorry, this is the point a, and say I have a function f, this is f of a. So, which means that okay, if f of a is equal to f of a prime, then a must be equal to a prime, right. So, there is one, it will always be distinct points, right. So, a will go to f of a, say some, maybe if I just take another point a prime, it will go to its own distinct point f of a prime. So, this guys will never, if these two points are equal, it means that these 2 points are equal to, right, or in other words, you know, maybe this a cannot map say into say some other point here. So, it cannot go this way, right. There cannot be any other a which associates which transforms under f to here. So, it will just be 1 to 1 as they call it. Okay. Now, similarly, if I look at what is called an onto function. So, this we would be familiar with this kind of terminology, right, 1 to 1 and onto. So, this means that if every element of b is in the image of some element of a under the function f. So, mathematically what it means. So, we look at b for all elements b belonging to b, sorry, all elements small b belonging to or coming from the set capital B. This b is equal to f of a for at least one a belonging to a, which means, so I just take any point here, say b1 till say bn, it should definitely come from some point, say a1 or whatever, right, in from the set A, right. Okay. So, now a map is called bijective if it is both 1 to 1 and onto, right, it is both injective and it is both surjective. Some of these proofs I will leave to you to prove the following, right. So, just take these, right? The composition of two injective functions is injective. Similarly, I can say that the composition of two surjective functions is surjective. Proofs are like just 2-line proofs. So, I will just expect you to work out yourself. If not, then we could discuss this over a forum. And therefore, we can also say that therefore, that as a consequence of these two statements, that if I have composition of two bijective functions, the resultant function will also be bijective. One interesting thing is of this map, if f is bijective, it essentially means that there exists. So, we have so far we have been talking of things going from A to B, right. Okay. So, what can the reverse exist, right, something here. So, it turns out that if f is bijective, then there exists a function from B to A. Now, f was defined on A to B. Now, if f is such that it is bijective, then there is something called f inverse for which the domain is B and the range is A or a subset of A. Now, this is called the inverse of A, right. Now, for a point B here, so this small b belonging to B, the capital B, under the function f inverse B will give me an element A, small a, which is a member of capital A, right. So, the notion of inverse. So, again we would have done this in some setting, in some math course, but again just to make it a little more formal. A little exercise again for yourself, just check if so given that f is both injective and surjective, what is f inverse? Is it do the same properties hold or not. Again, this should be like a 2-line proof. Okay, so before we go a little more formal, we will also define something called a field. So if you would remember something from set theory, you would know something called groups and rings and so on. But what we will use throughout this course is the notion of a field. Again, it's a little generalization of what we possibly already know. So a field is an object consisting of two binary operations. One is associated to an addition. Second one you can associate it to a multiplication, which just follows some axioms. And again, these axioms are nothing surprising. We would know this in one form or the other, but it's nice to write them down mathematically. So associative properties, you just add up A plus B and then add C is the same as you first add up B and C and add A to it. Commutative, I just say A plus B is equal to B plus A. Might sound trivial, but there are some interesting things that will go on over here. There will always exist an additive identity such that A plus 0 is additive identity, will just give me the same point A. Now for all elements in this field F, there will exist an inverse minus A such that A plus minus of this A, this is the inverse, will give me 0, and this 0 is the additive identity here. Similarly, we have rules associated with multiplication, same associative property A times B. If you multiply these two first and multiply by C is the same as first multiplying B with C and A. Commutative, A times B is B times A. There will always be a multiplicative identity which A times 1 will always give me A. There will be a multiplicative inverse and so on. Last interesting property is the distributions over the additive property. So if I take, say, all these elements again come from the field F, A, B and C. So if I take A multiplied by B plus C, it's same as A times B and A times C. Similarly, if I do a bit of the converse, so I just add up A and B first and multiply with C, it's the same as individually multiplying A with C and B with C. Okay, there are several examples here. So if I just take the real line, it will have it so satisfy all these properties. But if I just take the real line with the positive, say just the positive part, so this may not be a field because if I take a plus 5, there is no minus 5 associated. So R is a field, whereas R plus is not a field. And you can similarly construct several examples in higher dimension spaces and so on. So this is like just a brief prelude to the things we will start in linear algebra in the next course. So we will shortly look at vector spaces, non-vector spaces, matrix spaces, and then come with span and basis for a vector space. Again, you would have done this in some form or the other, maybe in your electromagnetics course or any other related course, but we will learn this a little more formally, generalize this, not restrict ourselves to 2 dimensions or even 3 dimensions, but just go to some n dimensional spaces and see how do we formally define elements on those spaces and what are the corresponding operators or corresponding operations that we can perform on those. So that will be in the next lecture. Thanks for listening.